Coming up, I am excited to welcome Dr. Jeffrey Funk. He will join us from Singapore. Dr. Jeff Funk is a retired professor and now independent consultant. He has written extensively on the economics of AI and other technologies, and is a recipient of the NTT Docomo Mobile Science Award for his early research on the mobile internet. His career as a professor and a consultant has focused on how new technologies emerge and diffuse. Dr. Funk is a visionary technology expert. After he moved to the National University of Singapore in 2007, he taught a unique course on the economics of new technologies that can be found on his SlideShare account that built from his Stanford University press book, Technology Change and the Rise of New Industries. The course and the supporting research present a methodology that can help entrepreneurs and investors avoid many of the loss-making businesses that currently comprise today's startup bubble. For instance, it identifies the challenges for ride-sharing, driverless vehicles, and AI, and proposes alternative designs and approaches for them that are still relevant today. Dr. Funk will share with us his thoughts on the controversial topic of, are AI breakthroughs far away? We need more augmentation. Welcome, Dr. Jeff Funk.
Hello, good to be here. So I have to get my slides set up here. Okay, so I'm going to get right into talking about how AI breakthroughs aren't working very well. And there's a number that have failed, from self-driving vehicles, or at least have not yet succeeded, self-driving vehicles. Of course, we all remember IBM Watson and other healthcare, criminal justice systems, chat box, GPT-3, text production, home flipping. These are some of the examples of breakthroughs that don't have enough nines. And what do I mean by nines? It's got to be 99.9999% effective, accurate, something in order to work. And a lot of times it isn't. And a lot of times it's going to take a long time to get there. So let's jump into the first problem. Autonomous vehicles have to be very safe before they're used. And that means they have to be 99.9999% safe, because that's what regular vehicles are. And human-driven vehicles have gotten safe over through decades of improvements in cars, in roads, lots of improvements. And you can look at other parts of society, like the virtual world of mature websites, Google and Gmail. They've taken 25 years to get to 99.999%. Or Amazon's web service, 99.99%. So these still haven't reached the 6 nines that we need for vehicles. And yet that was probably an easier problem. And so this is the first problem that's going to be hard to solve. But let's just say that it's solved, because there's a bigger one. And that bigger one is the capacity of the road system. How many vehicles can a city's transportation system handle per hour, for example, in peak traffic times? And what we found is that ride-hailing services, right? And you think of robotaxis. Robotaxis are a ride-hailing service that's without drivers. But the ride-hailing service increases the congestion in the city. It reduces the capacity of a city's transportation system. And you can see some numbers here. And the reason is obvious, because ride-hailing taxis have to drive around to find a passenger. Whereas if you're driving as a private driver, you're only in the car on the road when you're trying to get from A to B. But in the case of a ride-hailing vehicle, they're on the road much more than that, because they're looking for passengers. Now, they also have big losses, right? So that should also suggest to us that there's problems here. And another problem is that these ride-hailing vehicles may likely increase the congestion. They may likely reduce the capacity of a city's transportation system. And why do I say that? Because a few months ago, there was problems with Waymo's service in San Francisco where the cars stopped working temporarily. There were some outages, and they just kind of sat in traffic and you know, and cause these traffic jams. So these things are going to happen. Now, how long they happen and how often they happen, well, it's going to take time. It's the same with the safety argument. You really need to have a lot of nines in order for these services to work properly. And there are other breakthrough failures when you want IBM Watson, radiology. Turing Award winner Jeffrey Hinton said we shouldn't be studying for a radiologist. He said this back in 2016. Well, we need more radiologists now than we did in 2016. This isn't going to happen. Britain's national healthcare system is pulling back from AI. And there are other problems. I'll go into a little more detail on predicting crime, right? So, oops. So, you know, a lot of AI researchers claim that they've done something really great, like the University of Chicago claims that their algorithm predicts future crime, so it can help the police catch the criminals with 90% accuracy. Well, it's just basically explaining historical data. It's not actually predicting the real crimes, which a lot of people misunderstand. And they do that partly because we already use algorithms for a lot of things in the criminal justice system, setting bail, determining prison sentence, citing and parole, and they don't work. A lot of it's basically statistical coincidences. And these things are very scary because people are getting arrested. There's bail being set that's not accurate. Two Chinese, to take it even further, two Chinese researchers claim their computer algorithm predicts with about 90% accuracy whether a person is a criminal using photos. Well, nobody wants to be captured by that system because we don't have enough nines yet. We're not accurate enough to do these kinds of things. And let's just talk about facial recognition because this is widely used. Police use these facial recognition systems. A crime occurs and they look back at the footage, the camera footage, and then they see a person's face and then they try to match it to their database. And they don't set very high confidence levels. So according to the research, in some cases they would just set it down to 50% to see what happens. And obviously they were catching a lot of people who weren't the actual criminal. And you might say, well, how? Well, you know, what's the harm? You know, once they get in court, they're let off, and that's okay. Well, when someone's arrested, put in jail, they oftentimes lose their job. Sometimes just because they missed one day of work. So this is a very, very expensive. This is it isn't a very good system. And there's a lot of people's pictures in these databases. And there's more pictures than people because a lot of times the police will have pictures of you with a mustache, not with a mustache, with blonde hair, with black hair, and so on, right? Then there was Zillow's failure at home flipping. So Zillow thought that it could buy these houses and sell them better than a human could, right? So it would go around in these cities and the prices are going up. We're going up in 2020, 2021. So they bought the houses and then they sold them. The problem is that a lot of the predictions that the AI system was making, the algorithm was making, weren't very good. And why? Because it's a lot harder than just knowing the location and training your system on what and knowing the prices for houses that have been sold or bought around the house of interest. You know, the square footage and things like that, proximity to schools, parks, a lot of things. There's a lot of factors. So algorithms have trouble with weird layouts and, you know, next door beer bottles and things. Algorithms might even include home values go up because somebody bought a house to live next to their grandchildren or their children. So there's a lot of things that AI just can't do that well. And remember, it's got to do it well in order to replace humans. You really need a lot of nines, 6 nines oftentimes. How about GPT-3? So this chatbot, this system that you can converse with, and a lot of people have gotten excited by how well GPT-3 works because it can actually have a conversation. The problem is it doesn't work with 6 nines. It doesn't work with many nines at all, as many people have found out by conversing with the system and asking them various questions. So I have two conversations being done by my colleague Gary Smith, who just asked who is the president of the United States and then got all these weird answers that don't make any sense. He also asked, is it safe to walk upstairs on my hands if I wash them first? And he got all kinds of weird answers. So he's done this with many questions, got lots of weird answers. Gary Marcus has done this. Lots of people have done this. You really have to have a lot of nines. You really have to have high accuracy before these systems can work well. If you don't believe me, try using chatbots. Right? I've used a lot of chatbots, and they can never answer any hard questions. They're very easy questions. So they're basically not working very well. You might say, well, we can improve them, but it's hard. In fact, it's hard to train. A lot of systems don't work as well in the field as they do in the lab when they were trained. And why is that? Because things are different between the lab and the real world, right? So Andrew Nigg, he's a pretty famous guy. He's looked at, he's done training of AI on medical images, and he finds that it works pretty well in the lab. Or what I should really say is it doesn't work as well in the field as in the lab. And why? Because in the field, you have different machines, you have different operators, you have different hospitals. And it isn't because they're worse than the ones that he has in his lab. It's because they're different. And so the results don't work as well. So you think it works in the lab when you're training the system, but then you get out there in the real world and it doesn't work. That's just one problem with trying to improve the accuracy. The second problem, which is the bigger problem, is that it just takes so much computational requirements. It takes so many more computing resources to increase the accuracy, reduce the error rate. So this shows the computation required to achieve various error rates. And that computation leads to a lot of carbon emissions. It leads to a lot of costs, economic costs, money. You can see the error rates for different types of databases. One, ImageNet's pretty famous. So in ImageNet, there's a lot of images, and a lot of people will train their AI systems on that database because it's very big. But what people find is that if you try to reduce the error rate from 11.5% to 1.5% or to 1%, I'm sorry, to 5% or 1%, requires exponential levels of increase in computation and so on. It's not going to work. It costs too much money. And so when you see the poor results initially, well, it's going to be hard to improve it. And this is just going for 3 nines, right? 99, I should say 2 nines. What happens when you go for 6 nines? It gets harder. So these two problems threaten breakthroughs, all kinds of breakthroughs. It's not just the ones I've talked about here. And they're widely ignored by forecasters. You get these forecasters that just don't understand the amount of work it takes to go from the prototype to a real working system, to a system that works really well. And for example, here's 2 books, A World Without Work and The Rise of Robots. What they did was they first looked at academic papers. They said, well, did somebody write about something in an academic paper? Oh, yes, they say they can do it in an academic paper. And therefore, they assumed, okay, well, that's going to be widespread in a few years. They also looked at startups. There are other startups offering a product that does something. Oh, there is a startup that does this. Oh my gosh, okay. So that's going to be done. Those workers are going to lose their jobs. And as we all know, this hasn't happened, right? People aren't losing their jobs. It's hard. Unemployment is at record lows. And AI is not diffusing anywhere near as fast as these 2 authors thought it would. We know that it takes a very long time for laboratory work, university research, to actually get out in the real world. And if you don't believe me, think about how much change you see in your life every day, right? If these millions of papers, 2 million papers or so are published each year, if even a very small fraction of those, like 0.0001%, became true in the way that these two books claim they would, we would see change every day. But we don't. We don't see that kind of change because it takes a very long time. So their approach is very flawed. What we have to look at is what types of AI is succeeding, and then forecast from that. And what we see is these breakthroughs aren't. Instead, it's augmentation. I'm not going to talk a lot of augmentation. By the way, if you go to my LinkedIn, follow me on LinkedIn, you'll find every day I'm posting something at least once a week on AI. And so lots of things about problems with breakthroughs, successes of augmentation. And this is about startups. You look at AI startups, there's only two really broad, you would call broad-based AI startups, SoundHound and C3 AI. Very small revenues. They're all losing money, by the way. But all startups are losing money today. But they have very small market capitalizations too, despite the stock market being higher now than it was a couple of years ago, much higher still. They're very small market capitalizations, 1 to 2 billion. This is very small. And then I show a lot of other kind of enterprise software, a lot of software that includes some aspects of AI. Even these companies aren't doing that well. They all have losses. And only one has a market capitalization that would put it in the top 500 most valuable firms, CrowdStrike. And it's a big loss maker. So relying on startups, saying that, oh, startups are offering these kinds of products and services, therefore we're going to see this widespread in 5 years, 10 years, it's a very bad rule to use for predicting the future. What about other breakthroughs? Cancer, review paper says no. AI for drug discovery. Drug discovery is actually augmentation, but it's not doing that well. And again, you can look at some of my papers, some of the things I post on LinkedIn. It's a long ways away. Most of the protein folding only addresses a small part of drug discovery and drug development. Most of drug development is about trials. So we have to improve the quality of the drugs we discovered that we send to trial. But there's no evidence that AI is helping us do that, right? We get back to that question. How many nines? How many nines? If we want to replace people, we have to have a lot of nines. And on the other hand, you don't need so many nines for augmentation to work. It's a different problem. And it's a problem that can be done. There's a very successful case very recently for using AI to augment doctors, and concludes that doctors and AI together can do better at detecting breast cancer than doctors. Very big study. This is the type of example that I find. I say, okay, this is what AI can do, because you see, in their study, they showed that AI could be used to get rid of the easy ones. So the doctors don't have to look at the easy ones. Now, right now they have to because regulations force them to do. But you could envision over time that AI does the easy ones. Doctors don't have to look at them. You save a lot of time. Hey, that's good. That's a big improvement. So these things can happen, but we have to do augmentation. I want to leave you with one last slide. Right, this is data from the U.S. farming and manufacturing employment. So I put this up here because people, World Without Work and Rise of the Robots are all claiming that we're going to be out of work, which is ridiculous. And we've never seen that in the past. I mean, if you look at the past and look at how long it took for agricultural jobs to disappear, it was forever. You can see back down there, this is 1850, the slide starts with, the picture starts with, figure starts with. And really, it's really 1950 before it's lower than 10% of the U.S. employment. 100 years, right? Maybe it's less than that if you only measure from 1870 to 1880 when all this agricultural equipment was really starting to diffuse rapidly. Manufacturing, look at how many years it's taken for that unemployment to decrease. In addition, in manufacturing, it wasn't that all the factories got automated, we need more manufacturing workers. No, it's because we sent all the the manufacturing offshore. We bought things from China. We bought things from American factories in China or American factories elsewhere. And it's not just America that's doing this. This is the data on American unemployment. But this trend is also Europe, Japan, right? Every country is in. It takes decades to do this. So yes, we're going to see AI slowly diffuse, but it's going to be slowly, and it's mostly going to come through augmentation. It's not going to come through replacement. These arguments. So so forget about the breakthroughs. When people tell you about breakthroughs, be very suspicious. Be very suspicious because it's going to take years, and it's going to be mostly through augmentation. Thank you for your attention.
All right. Thank you so much, Dr. Funk, for your presentation. I'm sure many people who are worried about being replaced by robots will find that quite reassuring. I know that you've written extensively on the economics of AI and other technologies, which earned you the NTT DeComo Mobile Science Award for your research on the mobile internet. You also taught a course on the economics of new technologies that was based on your book, Technology and the Rise of New Industries. It sounds like a new movie, which explores why new industries emerge at specific moments in time. It highlights how technologies that experience exponential improvements in cost and performance have a greater chance of becoming new industries. What industries do you feel will demonstrate this type of growth in the coming years?
Well, you got to look for progress, right? It's progress, right? You say exponential growth. So you look for progress. So I look for progress every time in every single technology. And where do you see a lot of progress right now? Well, you see a lot of progress in batteries. I mean, Elon Musk has revolutionized electric vehicles. None of the traditional automakers could do that, but then he was able to increase the rate of improvement in the storage density of batteries. And lo and behold, electric vehicles are starting to be economical. So you see a rapid progress in that industry. But a lot of industry you don't. So we talk about AI. When you look at AI, you see the data that I presented earlier and how much it costs to go from 11.5% error rate to 5% or 1%. It costs so much. And so we don't really see rapid improvements there. Now, what you do see in AI is reductions in training time for the same accuracy. So this, again, is an argument for augmentation in that we're able to train better for a certain level of accuracy. It's when you try to improve the accuracy, reduce the error rate, that you get into these high costs. So then you see some progress. Now, it's mostly through better computers. Still, we get better computers. Moore's law is slowed, but we get better computers. A lot of other industries, though, we don't see this rapid rate. You look at virtual reality goggles, for example. They don't get smaller, right? They're the same size.
Right.
So there isn't a lot of examples. There's a big slowdown right now, which was first documented by Robert Gordon in his book on slowdowns in productivity. But there's a big slowdown in technology.
Right. When we talk about building AI at scale, we can't ignore the impact of training these large models on the environment. I remember there was a study in 2019 on deep learning's carbon footprint, and it found a single LLM releases the same quantity of carbon dioxide as a car over 5 years of driving. That's a lot of carbon. And more language models have been built, including GPT-3, Transformers, Megatron, Google Pathways, Lambda, and Bloom, which has 176 billion parameters. What do you think are a few ways that we can work to reduce carbon emissions while training these models?
Well, the problem is that if we're going to replace people, we're going to do this breakthrough approach of trying to replace people with AI, you're going to have very high accuracy, very low error rates. That's when you get into these problems with requiring lots more computation, which leads to a lot more carbon emissions, which I showed in one slide. And you mentioned that this is common to a lot of aspects of AI, and I agree. And so the way around it is to do augmentation. You don't try to go for nines. You try to go for fewer nines because you need fewer nines when you're just augmenting, because people will catch the hard ones, because people do the hard ones. So the solution to that problem is augmentation.
What would you say to those executives from different industries running to AI magic for solutions to their challenges, like carbon emission problems in airports and other challenges?
Yeah, it's funny that people think that, well, I can ask the AI system. They have this very simple view of AI that, oh, I'm going to ask them, ask the system, well, what should I do about reducing carbon emissions or something else? And obviously, this is ludicrous. It doesn't work that way. I mean, AI is just basically automated big data, right? You've got all this data, and it's garbage in, garbage out. You have to have the good data. You have to be asking the right questions. You have to ask the right questions first. Then you have to get the right data. Then you have to understand all the pitfalls of doing the data analysis wrong. And so at the very end, you're doing AI and AI after you've asked all the difficult questions yourself.
Being the mythbuster of the AI community, what metrics do you usually take into consideration to know if a certain AI project, principle, or concept has a strong basis in reality and is not just more AI hype?
Well, the first thing I look for is an example. Is it being used someplace? And it could be anything. It could be augmentation, that's fine. But is it being used? Not just a lab. They say in an academic paper, well, this can be done. And I'm immediately thinking, well, is it being used in the real world, and why not? And so let me just give you the case of AI discovery. So people talk about protein folding, and they say, oh, it can predict all these structures of proteins, and so therefore it's great for AI discovery. Well, then you look and you read some of the things by people who actually try to discover new drugs, and you find out that, well, protein folding is a small part of drug discovery. I mean, first of all, the protein has to match or I should say the target, whatever your drug that you develop has to match the protein. And AlphaFold can't do that. And the maker of AlphaFold, DeepMind, admits that, well, that's a really hard problem. So you see what they've done is they've chosen the easy problem, said, oh, we can do this, but it's not the bottleneck in the system. So you have to understand exactly what's the hardest thing, and then see if AI can do it. And so that's why in self-driving vehicles, I talked about safety, right? There's 1,000 things. People call them edge cases. There's all these edge. And so, yeah, the car can drive on the street, and you get in the car and it drives, and you say, wow, this is really amazing. This is really cool. And what I say to those people, I don't care if it's cool. I care if it's going to work 99.9999%. And you're going to have to be in that car a lot longer than that to see if it works. You're going to have to solve all those edge cases, and that's hard to do. So there's a lot of questions you have to ask. You have to look behind the curtain to find out if something works, and ask a lot of questions.
How long do you think it'll be before we have self-driving cars on the road that satisfy, that are good enough?
Well, as I said, it's going to take a long time for the safety issues to be solved. But to me, that's not the biggest. That's not the ultimate problem. The ultimate problem is that, well, let's step back. What benefit does it get to have a self-driving car? What benefit? Let's say you have one. What benefit do you get? Well, you could sleep in your car. You could look at your phone, as if we don't look at our phones enough. Is that really worth it? Is it really worth it that you get to sleep in the car in your 30-minute drive, or that you get to look at your phone? Is that worth the $100 billion, the few $1 billion a year that most of these self-driving vehicles spend on R&D each year? I have a hard time believing that. No, this isn't worth it. And then other people have said, okay, well, we're going to eliminate private cars. Okay, that's a benefit, because private cars take up a lot of parking spaces. a lot of parking spaces. So we eliminated private cars and everybody just somehow made their way to work without private cars. Well, then we'd eliminate all those parking spaces. Now the problem is that eliminating private cars requires some other service. So people have said, okay, these ride-sharing services, these are going to replace all these private cars, and then we can eliminate all these parking lots. And the problem is as I pointed out, the ride-sharing services increase the amount of congestion because you've got all these ride-sharing vehicles driving around looking for a passenger. So the capacity of the city's transportation system. And a lot of cities are very angry about this. And you're probably wondering, well, then why do they allow all these tests of driverless vehicles in the city? Because they don't decide. San Francisco doesn't decide whether those vehicles are allowed. No, because there's a Department of Motor Vehicles for California. The states determine whether cars are used, whether self-driving vehicles are allowed. And the city doesn't have a choice. The city's upset because they recognize that these self-driving vehicles have problems and thus lead to congestion, more congestion, right? More congestion. There's already congestion. So I have the suspicion that it's going to be more than years, it's decades, because this problem can't be solved. What we should be doing is using AI to reduce, or using some kind of system to reduce the distance between two cars. So you have communication between cars. Then you can increase the capacity of a city's transportation system. That's what we should be focused on. We shouldn't be focused on trying to eliminate the worker. We should be focused on trying to increase the capacity of the transportation system of a city. And one way to do that is to promote communication between vehicles. To me, that's a much better way. That's a very different way. And it's a way that requires a different set of skills than the automakers have. So I don't think we're going to see it. It's one.
Dr.
Just that thing there. I have pushed this for 8 years, ever since my students talked about driverless vehicles when I was back at NUS a long time ago. I recognized right away that, because if you've studied transportation at all, you know the problem is congestion. The problem isn't the driver. The problem isn't that the driver's cost is so heavy and people really want to sleep and look at their phones. No, the problem is congestion. And so I've been recommending this for 8 years. But the problem is automakers don't want this. They don't want a system like that.
All right. Dr. Jeffrey Funk, a visionary technology expert in artificial intelligence. On behalf of our audience, I'd like to thank you for sharing your thoughts, ideas, and supporting research on technology and the rise of industries. It helps us identify mistakes that entrepreneurs and investors make in an effort to rise through the ranks of today's startup bubble. We all look forward to following you on LinkedIn and other platforms to learn more about your research. Thank you again for being with us here today.
Thank you.